part 2 of Monday, March the 15th. So, what did we end up with X? X equaling my H plus concentration. What did we end up getting as the value? Somebody, I know you guys, everybody did it, so somebody tell me the number.
1.5 times 10 to the negative.
10 to the minus 4th molar. So then pH is equal to the negative log, 1.5 times 10 to the minus 4th is equal to 3.8, what? 2. All right, now we could have used the Henderson-Hasselbalch equation to do the exact same thing. You take the pH, it's going to equal the negative log of Ka, which is 1.4 times 10 to the minus 4th, plus the log of 11 over 0.12. You just plug all that into your calculator, and you're going to get the exact same answer. So, this was always on the equation sheet. When they redid the curriculum in 2013, starting in 2014, they had taken this off the equation sheet. They wanted you to do it, but then everybody said, hey, it's a standard way of solving it, and so the College Board brought it back a couple of years ago. So now it's back on your equation sheet, being able to use this to calculate the pH of a buffer. Sometimes they ask you to calculate this ratio. You just solve, you don't have to solve for X minus or HX, you just have to solve for the ratio. In other words, what this whole thing would equal to kind of go from there. Okay? Now, what would happen, what would be the difference between that buffer, or if I put in 1.2 molar and 1.1 molar? What's going to happen to my value of H plus? It's going to stay the same, right? Because that ratio is going to be exactly the same, so X is going to come out to the exact same number. But so what's going to be the difference between these two buffers, do you think? Again, let's just go back, let's refresh. What's the function, what's the purpose of a buffer? To resist changes in pH when acids or bases are added. Okay? Well, if I add acid to this, it's going to react with the X minus. So which one's going to be able to handle more H plus? 1.1. The 1.1, right? So it's going to have a greater buffer capacity, because once all of this is used up, we're no longer a buffer. Okay? Because we have to have some of that salt. So even though the pH would be the same, the buffer capacity is going to be greater because we have greater concentrations of both the acid and the base. So it can handle more acid or base being added without the pH changing as much significantly. Okay? So buffer capacity is how much acid, how much base can the buffer handle. Okay? The greater the concentrations of the acid and the salt, the greater the buffer capacity. The best buffer is a 50-50 mix, because then you can add equal amounts of either one, you know, and it can handle either acid or base equally without the pH changing. And at a 50-50 buffer, pH equals pKa. All right, so let's get practical with this. Everybody open up your book and turn to page 737. 737, and read that little article, the one-page article on page 737 about blood and buffers. Hey, Ben, Lauren better to kind of drop the paper behind you. So, what's the main buffer or buffering system in the blood? The sodium bicarbonate, HCO3, and the H2CO3. Why is the CO3 2 minus irrelevant or insignificant? Because it said H2CO3 is diprotic, but in this one, the CO3 2 minus is, insignificant. Why do you think that is? Because it is basically never forms, because H2CO3 is already a weak acid, therefore HCO3 is much rather going to go back to H2CO3 than it is to CO3 2 minus. So the amount of CO3 2 minus, remember, that's going to equal Ka. It's going to be very, very negligible. And so we can just totally ignore that. Now, so what happens when you begin to exercise and you begin breathing rapidly? Okay, it's the carbon dioxide concentration that's going to be how your body regulates the pH. Okay, because it's a gas, so the faster you breathe, the more CO2 you exhale. So what does that mean then about what that first reaction? Which way is it going to shift? If you're breathing fast, you're exhaling the CO2, right? So it's going to move to the right. Okay. So that's going to lower the pH, because when you're exercising, I'm not sure totally on the physiology here, but I mean, you're producing that lactic acid and the pH is starting to go up as you're exerting and doing the exercise. So that makes you just automatically breathe heavier. Then we have, as you are using up more and more of the oxygen, you're exhaling the CO2, but you're exercising, you're using up the oxygen, you go to the second equilibrium with the hemoglobin, and as you exhale, and your body's using up the oxygen, okay, then what does that equilibrium do? Shifts. That's what releases the oxygen in your cells for you to be able to function, okay? Because the oxygen's bonding to the hemoglobin. Something's got to cause it to release. Well, it's the Le Chatelier's principle that's going to push that reaction from right to left and cause the oxygen to be released into the cell as a result of low oxygen levels in your body. Okay, so when the hemoglobin that's got a lot of oxygen gets into the cell that's got low oxygen, well then that messes up, that's a stress on the equilibrium, and it's going to cause it to shift left, make more oxygen, that releases the oxygen from the hemoglobin, so then your cell can use it. Then actually the CO2 then attaches to it and you exhale, it brings it back to the lungs and you exhale it. Okay? So those three things, oxygen is consumed, causing equilibrium concentrations to shift to the left of that top one of the hemoglobin, releasing more O2. Large amounts of CO2 are produced by metabolism, which increases H+ and causes the equilibrium to shift to the left again. So the CO2, when you have a whole bunch of CO2, it shifts it to the left, makes a bunch of H+, a bunch of H+ pushes the other equilibrium hemoglobin to the left. Okay, so they're all working together. Our body is so complex. And then lastly, temperature effects, since it's exothermic, increasing the heat, pushes it back into endothermic direction from right to left. All of those things releasing oxygen into our bodies, into the cells, so our body can use it and we can function. Otherwise, you'd be running out of energy, running out of gas almost immediately. Okay? So it's really kind of amazing to me on how the body all works simultaneously. That's just one small equilibrium. That's just the oxygen in our cells. We got all the ions in the blood as far as the electrolytes and conducting electricity for the nerves. You got all the brain activity, all the equilibrium that has to go on there. Okay, so it's really quite amazing to think that all of this came to be just by chance and circumstance. That all of this came to be because a fish wanted to walk. I think it's easier to believe than, what's it called? Not creation. What's the other one when it's take God out of it, but you just, no, shoot. Anyway, some kind of higher order being or intelligence creating this. Anyway, that's just on how buffers are used in the body, okay? So that's gonna be huge. Let's kind of nutshell everything then. When you have a buffer, you always use the equation of either the acid or the base. The salt is going to be the product. It's the common ion, okay? So you don't go HX plus X minus trying to go to something. You don't try to mix the acid and the salt together. It's the equilibrium of the acid with some extra salt added in, or the equilibrium of the base with extra salt added in, okay? Buffers resist changes in pH. That's the whole point, okay? Now, one other thing on this article, though, notice the best buffers are 50-50, but do we have is the bicarbonate buffer in our bodies a 50-50? No. It's one is 20 times greater than the other. So notice that it says, okay, so for buffers to have a pH 7.4, the ratio of base to acid must be about 20. In normal blood plasma, the concentrations of HCO3 and H2CO3 are about 0.024 and 0.0012. Consequently, the buffer has a high capacity to neutralize additional acid because we have we got 20 times more of the base, okay? HCO3 minus is the conjugate base, 20 times more of it, so it can handle more acid, but the buffering capacity of the base, you know, I mean of the acid, the H2CO3 is very low. Okay, so it's really designed just to keep that H plus as we you know, exist, that H plus builds up, so we have to have a mechanism in order to use that up and shift the equilibrium. All right, that's buffers. If you want to make a correction in your notes way back when I was doing this base, it's going to be plus HOH. It's going to go to BH plus OH minus. I did it backwards. Okay, that's what that was supposed to be in your notes. When I say, oh, I really screwed that one up. Okay. Hey, I'm getting old. I'm allowed to have my senior moments. At least I still realize it. You know, I wish we could go some more slowly. I wish I could just give you time now just to sit and work and try and do some practice problems on these buffers. But we only have these 5 days, or hopefully all 5 days left to finish this whole unit. So we just got to push. Okay, it's darkest before dawn. Just realize that, hey, we're going to get to Friday, and then we're going to have a whole week off, and you're going to get to sleep whenever you want to. Okay? So, titrations. What do you guys remember from Chemistry 1? What's a titration? Okay? So in a titration, we're going to add some base. I don't even think I need to define it, but if I take HCl, I'm going to begin adding NaOH to it, and that's going to make what?
Water and NaCl.
NaCl. Plus water. All right? Now, if I start off with 1 molar, and let's just say 100 milliliters of this, and I'm going to want to titrate, I want to neutralize it with base. So if you remember this setup, you'll have an Erlenmeyer flask, you'll put your 100 milliliters of 1 molar HCl is in here, plus some phenolphthalein. Oops. Phenolphthalein is a great word to try to spell, because there's a bunch of totally wasted letters in there. Okay, what is phenolphthalein? It's an indicator. Remember, for this one, it is colorless in an acid. And what color in a base?
Pink.
Pink, magenta. Some say fuchsia, but I don't like to spell the word fuchsia because it starts looking like a bad word. So, I have this. Then I'm going to have my burette. Okay? And it's going to be filled with NaOH. So I'm going to begin dripping this down into here. When is the phenolphthalein going to change to magenta?
When the pH becomes basic.
Okay? When is that going to happen in terms of this reaction? Which means how much HCl will be left? None. We're going to add equal moles of the H plus and the OH minus, because the H plus is the acid, OH minus is the base, equal amounts to make neutral water. Then we have our neutral salt. Okay? So, if I start with 0.1 liters of HCl, how do I convert that to moles? Multiply by molarity, right? Which is pretty easy, 1 mole for every liter. Okay, so now that gives me moles of HCl. What's my mole ratio between HCl and NaOH? 1 to 1. So I need 1 mole of NaOH for every 1 mole of HCl. Which means that I need to add in 0.1 mole of OH minus. So then you would have to say, okay, well, how many milliliters? I'm going to measure how many milliliters it takes for it to turn to color, and I'm going to be able to determine the molarity of this by knowing the exact volume that it took. We're assuming 1 drop is going to cause the color to change. So at that point, then moles of H plus equal moles of OH minus. So times the volume of NaOH used. Okay? And that's going to equal the molarity of the NaOH. Actually, times 1 over the volume. Because molarity is moles per liter. Now that can be simplified. And for acids and bases, anybody remember the neutralization, the simplified reaction? Because this is 1 to 1, molarity times volume equals moles. So we can say molarity of the acid times the volume of the acid. That equals moles of acid. Is equal to the molarity of the base times the volume of the base. That's moles of base. So if we want to figure out in a titration how much it's going to take to neutralize, we can just use this simple equation right here. Now, if it took 100 milliliters, what would be the molarity of this one? 1, right? It'd be exactly the same. So it's gonna, if this is 1 molar NaOH, it's gonna take 100 milliliters to neutralize the 100 milliliters of 1 molar HCl. What if this were HC2H3O2 instead of HCl? Would it take more or less of the base to neutralize it? Okay, less is the logical answer. Because acetic acid is a weak acid. Okay? Based on what I'm saying, you would think it's going to be more. But it's not more.
The same.
It's the same. Because of Le Chatelier's principle, it's everywhere. HC2H3O2. It's going to break up into H plus and C2H3O2 minus. Now, if I start adding in base, we're only going to have a little bit of this, right? But if I have 0.1 or 1 molar of this, okay, the H plus is going to be real small. But the more OH I add, it's going to mix and make water. So what's that going to do to my equilibrium? Shifted to the right, right? So in other words, the OH minuses in a sense are pulling off all these hydrogens. They don't really want to come off in water, but you put them into a base, and the base is going to force the reaction to keep going right. As you keep removing the H plus out of the system, it's going to keep pushing it right until all the H pluses get pulled off. The only difference between a strong acid is they're already off here. Here, they got to get pulled off. But there's going to be, if you have the same amount of each one, if you have 100 milliliters of 1 molar, you have the same moles of H plus in each one. And the OH minus forces the reaction all the way to the right. And so it takes the same amount of base to neutralize a strong acid or a weak acid if you have the same amounts. That's a great AP question. They ask that all the time. All right. So, let's look at a problem. I'm back on that old sheet. This is what a titration curve is going to look like for a weak acid that is titrated with a strong base. So we're adding in milliliters of NaOH and we're tracking the pH as we go. Now how do I know that, number one, that this is starting up? If I'm just looking at the graph, how do I know it's a weak acid? What's the starting pH?
4.
Just less than 4, right? Just barely, it's almost around 4. A strong acid is going to be 0 to 1. Anything higher than that is going to be considered a weak acid. Okay? Now, notice how it stays relatively flat. That's because in this zone, we're creating a buffer. As we go through and we're doing this reaction, 30 milliliters of a weak monoprotic acid, so they didn't even say which one it is. Every time I take these breaks and erases, when you guys need to stretch, you need to breathe, you need to get yourself refocused, because I know today's long and arduous, but we got to get through it, okay? So, if I'm looking at a weak monoprotic acid, HX, I'm going to H plus X minus. Now, we're going to have to know the pH at 4 places on this graph. We're going to have to know it at the beginning. That's going to be your straight Ka problem. The Ka, do they give you on this one? No. Okay? So let's just say the Ka is the classic 1.8 times 10 to the minus 5. how would I calculate the pH of a 0.1 molar solution of HX? What is the pH? What do we do?
The square root of 0.1 times the Kn.
Square root of 0.1 times 1.8 times 10 to the minus 5 is going to equal, somebody give me a number, we've done it before, but
1.36
okay, so that's my H plus, which is also the same as my X minus. Now, generally, we don't care about X minus. So, but it's going to be a very, very small amount, right? So at this point, in our equilibrium, we have way more HX than we do H plus or X minus, right? Now, so if I want the pH, negative log of that, what's that equal? 2.86. Okay? Now, that's at the start. But as I begin to add OH minus, what's happening to this reaction? What's the OH minus reacting with here? The H plus, right? So what's it doing then as far as to the X minus concentration? It's going up, and that's going down, right? It's forcing the reaction to the right. But for every OH minus that's taken out, more is being replaced. So we're producing the salt of the weak acid. So what are we creating? A buffer. So as we're going there, so now we have to figure out, well, from the graph, we can always tell wherever the steep part of the graph is, that's going to be your equivalence point. That's going to be where acid equals base at the steep part of the graph. So I know that that's going to be, well, let's just say right in the middle of that, I'm going to call it 24. Okay? 24 milliliters is how much it's going to take totally to neutralize it. So what's halfway? 12 milliliters. Okay? At 12 milliliters, at halfway, how much of this has reacted? So now I'm at 0.05. And what's this going to be? 0.05. So now, what we call the half equivalence point. I tend to call it the midpoint. The halfway point. There is a 50-50 buffer. So what does pH equal? The pKa. Therefore, pH equals pKa. This question, I guarantee this question is going to be asked. I guarantee it's asked on my test, but I guarantee it's asked on the AP test at some point, maybe twice. Okay? So, at my equivalence point, right here, at 12, okay, this is really going to be my 12.5 or you know, I don't know, this is my halfway point right here. What's my pH? Approximately 5, right? So if the pH is 5, what's the Ka going to be? 10 to the negative 5. So Ka is going to equal 10 to the negative 5 on that particular. So I can use this. So explain how this curve can be used to determine the molarity of the acid. Okay? We can use the equivalence one. We'll come back to that one. Okay? But at the halfway point, notice again, so at this point right here, from here to here, you have more HX in the solution than you do H plus or X minus. At the midpoint, what's true about HX and X minus? They're the same. As we continue past the midpoint, now at this point, which one's greater? HX or H plus and X minus? X minus, right? Until finally, here at the equivalence point, now we've exceeded the buffer. We've used up all of our HX. Now it's just going to be over here, okay? So now it's just X minus. The OH minus all got used up because right at that one drop, right at the equivalence point, the OH, the last drop of OH reacted with the last bits of H plus and made water, leaving just X minus in the solution. Then once we get past the equivalence point, now we're just adding excess NaOH. So now we just have all the pH is going to be dependent upon this. Remember we said in a mixture of a weak acid and a strong acid, you look at the strong acid, or a weak base and a strong base, you just use the pH of the strong base. Well, once we get here, we have X minus, which is the conjugate base, but it's real weak. And then we're adding in a whole bunch of strong base, NaOH. So now the pH is really just dependent upon the concentration of the NaOH. We have some X minus still in the present, but it's the presence of the high quantity of OH minus from this that determines the actual pH. That's why there's this huge increase right off the bat, because all of your buffer is gone, and now we're just adding in OH, and it's just building up rapidly. So this is going to be the shape of a curve of any weak acid, strong base. We can find the pH here, just doing Ka. We can find here, because pH equals pKa. At the equivalence point, that's where moles of HX equals moles of NaOH. And we can figure out the molarity, MaVa is equal to MbVb. Okay? I want you to underline this word, standardized. Anybody want to guess what that word, what a standardized solution of NaOH means? No, that's a good guess.
Nothing else in it.
It is definitely pure, but it just means an exact concentration. You know the exact concentration. It's been standardized. It's been measured against. We know the exact concentration. So we know the concentration of the NaOH. In other words, we know the molarity of the base. From our graph, we can measure the volume of the base that it took. And I know the volume of the acid that we started with, 30 milliliters. So I can then figure out what the molarity of the acid must have been. Okay? But unless you know what the term standardized solution means, you don't know that you know the molarity of the base. But anytime you have a standard solution, that means you know the molarity. All right. Let's look at another one. We are ready to do some 2015 question. I'll make copies and have this for you tomorrow. I really didn't think I was gonna get to titrations today. But I'm pushing through. I'm erasing, so you're breathing, you're stretching, you're getting your brain back engaged. So, potassium sorbate is commonly added to diet soft drinks, so that means I've drank a bunch of potassium sorbate as preservative. I'm hoping that if I eat enough preservatives that it'll slow the aging process. That's kind of my goal, I figure. But nutritionally, it's probably not the best way to go about things. A stock solution of potassium sorbate of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with 1.25 molar HCl using both an indicator and a pH meter. The value of Ka for sorbic acid is this. Write the net ionic equation for the reaction of this plus this. What is this? It's a salt. Is it going to be an acidic, basic, or neutral salt?
Basic.
How do I know it? Somebody tell me. How do I know it's basic?
Because it's gonna attract an H plus.
All right, but when I'm just looking at this, how do I determine that this is basic? K came from which base? KOH, which is a strong base, right? H, this is not one of our 6 strong acids, which means that this is going to be a strong base and a weak acid, which means it's going to be a basic salt. So I'm going to ignore, when I say the net ionic, I'm ignoring the potassium, I'm ignoring the Cl minus. So I am simply going to say, what is it? It's complicated. C6H7O2. C6H7O2 minus plus H plus goes to HC6H7O2. So that's my net ionic equation. So we got to be able to recognize that we have a salt that's basic. We've already learned how to do that. Okay. Now we're going to do an acid-base neutralization with that basic salt plus the acid is going to make the base. Now if we put in H3O plus here, we get a plus H2O. Okay. Now a total of 29.95 milliliters of H plus, 29.95 milliliters. Again, the H plus came from the HCl, so we're just ignoring the Cl. So it's important to see that the H plus is this thing right here. And it's 1.25 molar. Calculate it, and does it say 45 milliliters of this was used? Okay, so that's given right up here. We used 45 milliliters of it. So the question is asking, calculate the molarity of this. So the molarity, so how do I do that? MA, VA is equal to MB, BB. This is part B. So I'm going to say the molarity of the acid is going to equal 1.25 molar. Now the good news is this is a ratio. I can leave it in milliliters. 29.95 divided by 45. As long as these two units are the same, it doesn't matter what they are, the volume. Because if you multiply each of them by, or divide each of them by 1,000, you're going to get the same ratio. What do we get? I didn't hear that, what? 0.832. Do we agree with that number? All right, now C. Here we haven't talked about C yet, but let's go ahead and just talk about C. We want to pick an indicator. These indicators are actually weak acids and weak bases, and so it just depends upon which one is in greater concentration. You always want to find the pK for the best indicator. You want it to change colors at the pH around the equivalence point. You can determine that by taking the pKa of each of these are weak acids, so they all have Ka, so these are the pKa. We want to find the one that's closest to 2.54. Well, the one that's closest to 2.54 is thionyl blue. So, I mean, that's how you do that. You want to find, for the indicator, you want the pKa of the indicator to be as close to the pH at the equivalence point. That's how you pick. There's no math involved. You just have to know that concept. That's how you can pick, because we're going to find that the pH at the equivalence point is going to vary. So C, since the pKa of thionyl blue is closest to 2.54, right, it would be the best indicator. Now D, calculate the pH at the half equivalence point. What does pH at half equivalence point equal? pKa, right? At the half equivalence point, pH equals pKa. We just know that. So the pH equals pKa, which is going to equal the negative log of the Ka, which is given as what Ka is given? In this case, we want, it's not going to be the pH, because this is a what? A base, okay? So therefore, POH is equal to the negative log of what? PKB. So if I'm given the Ka, how do I find the Kb? Because Ka times Kb equals Kw. So the Kb of C6H7O2 minus is equal to 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 4th.
5.88 times 10 to the 18.
Okay, so they kind of threw in here at the half equivalence point, but they gave you the Ka, so they want you to be able to know how to find the Kb. It's very important you understand that this is a base. You cannot use Ka for a base. It's got to be Kb. So now I say the POH is equal to the negative log of the Kb, not the PKB, the negative log of Kb, which is 5.88 times 10 to the minus 10. .23. Therefore, the pH is equal to 4.77. Now notice that that's way below 7, okay? But that just means that this is very weakly basic. You're adding the H+, it's bringing the pH down quickly, okay? And now we're at 4.77. Pick up tomorrow more on these graphs, but we're pretty much there. We just have to learn all these little nuances, okay? So have a great day and go Jags.